So today I will talk about, my name is Vladimir. Today I will have a talk about branching random walks in random medium. And first of all, I want to thank the organizers of this conference. I'm very glad to be here. Thank you very much. Also, I want to thank my scientific advisor, Елена Борисовна Яровая, Professor Елена Борисовна Яровая, and Professor Stanislav Molchanov for the suggestion of the theme and very fruitful discussions about it. We will consider, I will sometimes draw something on the board. We will consider a very simple task. We will have one-dimensional lattice on which there is some system of particles. The particles behave just like in branching random walk. They can walk to the neighboring points. They can branch, they can split into two. They can die with some rules that we will describe a little bit later. But before the process begins, some random medium is realized on this lattice, and which, okay, let us go to the next slide. The branching and the branching intensities of the medium is governed by some random variable, which is realized before the initial time. So it's like a stationary random variables. These random variables is constructed as follows. At 0, there is some splitting intensity, non-random, equal to lambda capital. Outside of the 0, there is some random intensities of dying defined on the slide, which are random. With probability p, these random variables are equal to 0. Each one is equal to 0, and with the probability 1 minus p, it is some random variable. It is very convenient to think about it as a uniform random variable on the segment 0, 1. But in general case, it's just some variable with the support on the 0, 1 with positive density. So it looks like you can see on the slide. This is some example of the random medium. This is just some generated medium, and here it goes in some random way. At 0, we have some intensity of splitting non-random, and outside of the 0, we have some intensity of dying, which is random. We will talk essential. I again need to emphasize that this is a random medium. So in some other experiments, we will have another copy of this medium with the same lambda, but some different intensities of death and outside of the 0. So it's something like that. Another random realization. Now we already described full evolution of the particles on this lattice, and it is pretty simple. So if particle stays, if there is a particle at 0, it waits for some exponential time, and then jumps to the neighboring points or splits into 2. If the particle is located outside of the 0, it again waits for some exponential time, which depends on the point, and then jumps to the neighboring points or splits into 2. So this is just a simple branching random walk. What we are interested into? Before this, of course, this system is not completely new. The idea of branching random walks in random medium apparently for the first time was described in the series of works by Zildovich, Molchanov, Rozmakin, and Sokolov in the 1980s. Then there was a big evolution of this theme, and in the not so long time ago, there is again some work in this area. For example, the Elena Chernousov's work, which is quite resembles with our current. There is a Happy Islands and something about it, and a bunch of our works. But all these works, in contrast to the current model, are considered a very general model. For example, it's always multidimensional lattice. It's always homogeneous random potentials with some distribution. And here we consider some simple model. So a very simple lattice, very simple symmetric branching random walk, and very simple distribution of randomness. Because of this, we want to derive some precise results, even maybe non-asymptotic results about our model. And in these works, there is only some general results about some asymptotic things and so on. So we will talk about, of course, the average number of particles. It is some intuitive variable. So on this medium, we of course can put particle without loss of generality. Let us think that at the initial time there is one particle at 0. So we put some particle at 0. We have some evolution of the system. This is a number of particles, for example, at 0. Again, we can regenerate the system, have some evolutions, and we have the average number of particles. This number of particles will be different with each regeneration of medium. So this number of particles, because there is some other evolutions on this medium, this number of particles is a random variable with respect to the medium. We will denote it by such a lengthy notation. Let me describe it. This thing means that we are interested in average number of particles at time t at point y, while at the starting time at point x there was one particle, and the medium is generated with realization omega. We are interested in the two main questions. First is somehow maybe can be considered as a simple question, which how large must be lambda to the medium, which is the values lambda. I don't know how to tell it. How large must be lambda that we will have exponential growth independently of the mu realizations, because they are random. So how much must be lambda? So there will be almost surely exponential growth. And the other one is about okay, if we do not have almost surely exponential growth, which is the probability of exponential growth for some fixed lambda? We will, so this is our today's questions, and we will show you some results about it. First of all, of course, we need to write our common partial differential equation, which describes the evolution of M1. The evolution of M1 is some okay. The evolution of M1 is described by some diffusion, which is very simple in our case, and some random potential, which is in our case just a multiplication by some function, some bounded function. We will we will make the following again common notation. Just we will consider the operator H. I need to emphasize that this is a random operator. We will rewrite the equation in the following way. And this equation suggests that the quantity M1 is experiencing the exponential growth if there is a positive principal eigenvalue of the operator H. This is just like common in this field, and it can be just derived. And this eigenvalue will define the rate of exponential growth. Okay, therefore we just need to evaluate the spectre of the operator H. We will do this. Again, H is some operator. Let's consider some auxiliary operator, which is more simple than H. It's just an diffusion minus random variable at each point. it is a random operator, but it can be shown that the spectrum of this operator is not random and is equal to the segment that you see on the slide. There is just a simple idea that the operator kappa delta have a negative spectrum, minus mu have again a negative spectrum. They somehow collide, and we just need to show that this colliding is equal to this. And our operator H is just a one-point random perturbation of operator H mu sub mu. Therefore, we can expect that there can be only one eigenvalue. Maybe there is one positive eigenvalue and nothing more. All other spectrum is just the essential spectrum, and this lambda is the eigenvalue that we desire to evaluate. Yeah. Mu is equal to it is like this. It is bounded on the segment from 0 to 1. So yeah, for Alex, yes, for OX. No, it depends. The support of mu is 0-1 segments. So we can think about mu as just like what here. Here, mu is just an operator of multiplication. So the spectrum of mu is just the множество значений. Set of values of mu, yes. Yes, oh, from 0 to 1. Yes, kappa delta minus mu. The spectrum. No, the spectrum of kappa delta. Yes, it's from Newton. -1, it is the dependence of mu in -1. This is just a shift of spectrum. Not a shift, but some like shift and blur of spectrum. So it's still the 0 is still in the spectrum. Yeah. So all idea of this is just that now we can just write the eigenvalue problem. And if there is a solution, positive solution for this eigenvalue problem, then this solution is our lambda that we are trying to evaluate. If there is no solution, therefore there is no positive lambda. Okay, so we need to solve this. And because of the form of the potential, it is more, of course, it is more convenient to write this problem using two equations. Equation in 0 at 0 and equation at non-zero. And there is I think, a magnificent fact. Let us consider the equation not at 0. The solution of this equation can be written in the following by the following form. It's just some sum over the paths from x to 0, which do not intersect 0. And each path consists of some series of penalties. So it's just a penalty for which point in which path goes. It can be just shown by substituting this formula to the equation. At first glance, it is still a non-constructive thing, like some paths, some penalties. Therefore, let us a little bit simplify the problem and try to do the following. The black is some our random medium. Let's just bound this from above and from below by some non-random mediums, blue and orange. Every black random medium is just bounded between them. Therefore, it's if there is a positive eigenvalue for we need to, if there is a positive eigenvalue for the blue medium, of course, there is a positive eigenvalue for the black medium. If there is a positive eigenvalue for the black medium, it is, of course, less than the positive eigenvalue for the orange medium. So it's just a bounds for the eigenvalue. And these bounds using this formula can be explicitly derived. We just need to substitute mu with some non-random values, and this is just the series which can be combinatorically solved using combinatorics. And this is because the number of paths from 1 to 0 can be rewritten as a Catalan number. Everything is exactly calculated. The same can be done for the blue medium. And it appears that we have solved, we can just substitute this solution to these equations. And therefore, we just have solved our problem with the following result. So if the solution that you can see on the screen, if the condition that you can see on the screen is met, then there is a positive eigenvalue. If it not, almost surely, if it is not met, then it may be some positive eigenvalue, but not almost surely. So in some mediums it will be, in some it will be not. It won't be. And this is pretty simple. I need to emphasize that this condition is derived without using any Fourier transforms, without any green functions, just purely combinatorics, which is pretty simple. Of course, we want to calculate if these bounds are somehow precise, because we have some bounds and maybe they are just not precise at all. To do this, this condition is condition 1. Sorry. Yes. If there is a positive eigenvalue, it is bounded by these bounds. Yes. If there is no, it is bounded from below with 0. So it's like, yeah. We used some, we want to estimate the precision of the conditions, and we just use the numerical estimation. We did some, for example, let us just fix some parameters with the red, lambda equal to 3, kappa equal to 4, and some probability of, let me just remind that P is probability of turning off the point. So if with probability P, the neighboring to non-zero, some point outside of the 0 is just a point where nothing is undergone, non-splitting, no death. So if we just fix the parameters of the medium, we can do some numerical tricks and solve the equation for the eigenvalues, this equation, just numerically for some generated medium. Then we can regenerate medium, solve again this equation, regenerate, solve, do this a large amount of times, and just plot the histogram of the obtained eigenvalues. And for example, for the red, you can see the distribution of the eigenvalues in the medium with these parameters. We are interested in only positive eigenvalue. Yes. So for the blue medium, the right blue, which is going to the negative side, it's just it is not interesting for us. It's just some numerical estimation. We show that in okay, let's consider the blue medium with lambda equal to 1, kappa equal to 4, and p equal to 0.5. So for some realizations of this medium, for some generations, there is only there is no positive eigenvalue. The solution for the eigenvalue problem is negative. So there is no exponential growth. Only one. The operator H has only one value because it is just can be considered as a one-point perturbation of some random operator which have no eigenvalues. I mean, yes, it has an almost eigenvalues. They are there is series of can I just explain it Russian? H mu имеет вот этот спектр, который состоит из почти собственных значений. Он существенный, и там они не в точности собственные значения, а есть последовательность функций, которая приближается.
Оно гораздо более сложное. Но тем не менее это все равно правда.
Сейчас. Нет, где? Нет, они всюду плотны вот в этом отрезочке. Это точно собственное значение. Я подумаю об этом, да. Сейчас я могу путать. Да, надо еще раз. Это не дискретный спектр, да. То есть это... Он всюду плотен, да. Сейчас, ну вот, есть... Так, надо здесь подумать. Ну вот если мы, if we write the problem for the eigenvalues and try to solve it, we will obtain the lambda which is not in this essential spectrum. And this is the lambda which is, yes, which is from the... Yes. Of course, because H sub mu is, has a non-positive spectrum, we just, yes. And some eigenvalue which is positive is always outside of the spectrum. And during the the numerical simulation, we are trying to find this lambda, and if it is negative, это, не смотрите туда, это типа, это численный алгоритм, он просто иногда, just for the visualization. So we can think about, there is, for the blue medium, there is just only sometimes a positive value, and all like 50% of the realization has no positive eigenvalue. Вот это все решения задачи на собственные значения. Это все решения, это решение задачи на собственные значения для каждой следующей случайной среды. Ну, там взято миллион случайных сред, и для каждой решено одно. Ну, вот грубо говоря, если отрицательное решение есть, это вы правы, нехороший рисунок. Сейчас. Их нет. Имеется в виду, что если вот на картинке появилось отрицательное число, значит положительного собственного значения нет в среде вообще. Вот мы говорим, мы написали вот так. Что-то там и вот это. И вот численным решением мы пытаемся найти вот эту штуку. Вот. Да. Значит, положительных нет. Значит, численное решение дало какой-то бред. Отрицательное что-то там есть, да. Ну, это мы его, считайте, что его нет. Нет, да, вы правы. Грубо говоря, если нашлось нас они не интересуют, потому что нас интересует только положительные. Но это... Я согласен.
Мы покажем, что...
Да, это артефакт численного решения. Да, то есть мы можем думать об этом так. So the main idea of this picture is that let's consider only positive eigenvalues. Our boundaries on the top is not precise at all. So we have a vast amount of space, for example, for the green medium from the end of the histogram to the end. Our estimations is not precise. To make them somehow precise, we need to make them random. So we of course, for the green medium, there can be eigenvalue equal for 1 for a very lucky realization of medium. But this is this can be with the negligible probability. We need to estimate this negligible probability, and to do this, we use some techniques that have already been told about today by Elena Chernousova. For example, we use large islands. Let us consider that the lambda is not very big. What can save this medium and grant it the exponential growth? Only very large random islands around the zero. Therefore, we just need to do some calculations and show, for example, this result. For if there is a very large island round medium, and there is a positive eigenvalue, then this eigenvalue is bounded from below by this. But this result is not interesting because we are interested in the when there is a positive eigenvalue on this island. If there is some eigenvalue, that is okay, but we're interested in when it is. And we do not have any results on it except for, yeah. В пределе. For a very large, yes, this is L. That means for a very large island, it is true. L is bounded. Yes. So, I mean, this is
even dramatic.
No, I mean, this is a lower bound. Yes, or yes. It is a lower asymptotic bound. For some very large L, it is true. For which one there is starting from a, yes, starting from some L. This is, yes, thank you very much. It is more. And we have the this. This is abomination. We can write the exact condition for the L island. So let's fix not asymptotic, but some fixed L. We need to solve this problem. If it is solvable, then it grants the lower bound for the L island. If it is unsolvable, if the series diverge, then there is no positive eigenvalue. At first, this problem has no like any interest for us, but it can be solved numerically very fast. So it is just algorithm to, because this is a power series, they are converge to diverge very fast. So this is an exact numerical algorithm for the exact island to, yeah. Finite interval. Yeah, I mean that if let us consider our random variable, random medium, which has.
Когда в некоторых случаях, которые пока вы криптологические, вам приходится шкалу по эпсилон менять.
I don't think it's for us. So if we have some L island and some random variables around it, then the eigenvalue for this medium is bounded from above by this. What's the solution of this? So there is like no boundary conditions, something very random around this L island. Oh, yeah, here. This is again purely numerically interesting result, and there is a different type of the same problem. For example, again, consider lambda being not very much. What can kill the medium in this case? The medium can be killed by the nearest very vast pits. Yeah, both of them. If both of them converged, yes. Thank you. Yes. If this equation have sense, then. Yeah, sure. Там 2 слайда. Да. So just for the main idea here is let us consider 2 pits around 0. If this pit is deep enough, the medium will die. How much enough? This enough. So if there is a very pretty and closed form condition, if we consider medium with, like on this picture, with 2 points tangents to 0, with some intensities of dying, the medium will undergo exponential growth only if this condition is true. And this is, of course, much more interesting, like some science sense. If and only if, yes, if and only if this condition is true. So that's all. I will glad to answer any questions. Thank you very much.
We have more than one source. Finite number. Yeah.
Then our technique breaks.
Will it be
That's all.
qualitatively, will it be similar or you don't know?
Intuition tells that yes, it will qualitatively similar. Yes. Yes, but the number of trajectories will be combinatorically, I think, like very big.
Plus one and minus one. Yeah.
Yes, but we are mainly operating by this combinatorical form, and if there is 2 points, it will undergo some very strange like interactions between. And yes, it is.
But it might be.
Yes, it is very interesting. Yes, indeed. Yes, we need to. This is the parts of the problem at non-zero. We need to solve it at non-zero and then substitute to the part at the zero to find the eigenvalue. Yes. Yes. No, да, мы не ищем настоящее собственное значение. Вот здесь мы ищем только оценку. Yeah, we have the boundary. Не, ну U-orange это решение проблемы вне нуля для оранжевой среды. Да, потом мы, да. Потом мы все равно вынуждены поставить 0, чтобы получить решение для этой же оранжевой среды. Да. Yeah, so if there are no questions, thank you very much again.